My name is Matthew, and today we're going to be discussing linear dependence. And in particular, we're going to be covering two different definitions of linear dependence with examples for each of those definitions. So, to go ahead and get started, let's go over the first definition of linear dependence. So, a set of vectors v1 all the way to vn is linearly dependent if there exist scalars alpha 1 all the way to alpha n such that alpha 1 times v1 all the way to alpha n times vn equals the zero vector, and not all of the alpha values are equal to 0. So basically, we're interested in finding out if there's some linear combination of the vectors v1 to vn such that it equals the zero vector and not all of the alpha values are equal to 0. So let's see an example. Alright, so we want to know if this set of vectors 1, 2, and 3, 6 is linearly dependent. So we can use the definition that we just saw and assign some scalar values to each of the vectors. So we can assign the scalar c1 to the vector 1, 2, and we can assign the scalar c2 to the vector 3, 6. So going back up to the definition, we want to know, is there some linear combination of these vectors such that it equals the zero vector? So we can just set our equation equal to the zero vector. So now, can you see any values for c1 and c2 such that it would produce the zero vector? Well, one possible value for c1 and c2, if we set c1 is equal to -3 and c2 is just equal to 1, let's see what we get. So -3 times 1, 2 plus 3, 6. Let's see. So that's just equal to the vector -3, -6 plus 3, 6, which does indeed equal the zero vector. So since we satisfied the definition of linear dependence, these two vectors are linearly dependent. Therefore, the vectors 1, 2, and 3, 6 is linearly dependent. And if we had scalars such that these were both 0, then that would not satisfy the definition of linear dependence because we have to have some alpha values that are not equal to 0. So since we found these two alpha values that are not equal to 0, and we took linear combinations of the vectors in our set, and we got the zero vector, we can now determine that these two vectors are linearly dependent. Just to look at a graphical representation of what's going on here, if we take the vector 1, 2 and plot it down here, let me grab a different color. So the vector 1, 2 is this vector right here. And let me grab a different color for 3, 6. 3, 6 is the vector right here. And in fact, these two vectors look like they're on the same exact line. So if we extend this line that these two vectors are covering, we see that both of these vectors are on the same line. And that is a representation of linear dependence. If you take linear combinations of these two vectors, those linear combinations will only lie along this line. So that is why these two vectors are linearly dependent. All right, let's see another definition of linear dependence. So the second definition, a set of vectors v1 to vn is linearly dependent if there exists an index I and scalars alpha j's such that some vector vi is equal to the sum of is equal to a linear combination of the other vectors in the set. So, in other words, a set of vectors is linearly dependent if one of the vectors could be written as a linear combination of the rest of the vectors. So back to our first example, we know that 1, 2 is just, or actually 3, 6 is actually a multiple of the vector 1, 2. If you just multiply 1, 2 by 3, you get 3, 6. So in this case, you can represent this vector 3, 6 as a combination of this first vector 1, 2. So let's look at a different example. So let's look at these two vectors, negative 1, negative 3, and 5, 1. And going back to our second definition, a set of vectors is linearly dependent if one of the vectors can be written as a linear combination of the rest of the vectors. Looking at these two, it doesn't look like either of these vectors is a multiple of the other. So in fact, each one of the vectors cannot be written as a combination of the other vectors. So therefore, we can determine no, they are not linearly dependent. So in that case, they are linearly independent. All right, let's just take a look at what that looks like graphically. So we have the vector negative 1, negative 3, and 5, 1. So let's first plot negative 1, negative 3. Down here. And our other vector was 5, 1. So right over here. Now in this case, as opposed to the previous case in the first example, these two vectors are not on the same line. So in other words, you can take linear combinations of these two vectors, and essentially you can take any linear combination of those two vectors, and you can get any vector in R2. So basically, if I take this vector and add 1 to it, if I take this vector and add this vector, I just get this vector right here. So essentially, using these two vectors, I can get anywhere on this plane. And that's what it means to be linearly independent, as opposed to these two vectors, which are linearly dependent. They can only span this line. You can only get points on this line. So there is a brief overview of what linear dependence and linear independence is. And I hope you found this video useful. Thanks for watching.